Hello and welcome to the Drone Builders Collective. Whether you are tightening your very first bolt or fine-tuning a custom carbon fiber frame, you have found your crew. Before we dive into the hangar today, make sure to hit that like and subscribe button on whatever platform you are listening on. That way, you never miss a lesson in building the ultimate flight machine. This is the podcast where we break down the high-flying world of aerospace engineering into pieces you can actually use on your workbench. Every single week, we dive deep into the art and science of making things fly. We will explore aerodynamic principles, aircraft design, and robotic functions. You don't need a fancy degree to build something incredible. You just need the drive to learn, create, and launch.
Welcome to Aerodynamics and Flight Lesson 2, Wings and Lift, Airflow, Pressure, and Momentum. Now that we know the four forces, it's time to look at the one that does a lot of the heavy lifting literally. We need to understand how a wing creates lift. Before that, it helps to name the parts of a wing. A cross-section of a wing is called an airfoil. Every airfoil has the same basic anatomy. The rounded front edge is the leading edge. The sharp or converging rear edge is the trailing edge. The straight line connecting them defines the chord, which is the wing's nominal front-to-back dimension. The airfoil's midline, the mean camber line, describes how much the wing curves. A symmetric airfoil has a straight camber line. A cambered airfoil has a curved one. The thickness describes how fat the airfoil is relative to its chord. So, when an engineer talks about a wing, they mean a specific combination of camber, thickness, chord, planform, and angle. Each feature exists to produce a particular aerodynamic outcome. What angle of attack really means. The single most important setting for any airfoil is its angle of attack. Despite the name, angle of attack is not the angle between the wing and the horizon. It is the angle between the chord line of the wing and the direction of the oncoming airflow, called the relative wind. When an aircraft sits on a runway, its wing may already be tilted slightly relative to the horizon. That static tilt is the wing's incidence or rigging angle. Once the aircraft is flying, what drives lift is the angle between the wing chord and the actual airflow over it, which changes as the aircraft pitches, banks, speeds up, or flies through rising or sinking air. In steady, level flight, the aircraft flies at a relatively small angle of attack off a few degrees. To fly faster at the same weight and altitude, the pilot lowers the nose to reduce angle of attack, because less angle is needed to generate the necessary lift at higher speed. To fly more slowly, the pilot raises the nose to increase angle of attack, because more angle is required to generate enough lift at lower speed. This is why the phrase pull back on the stick to go up is a simplification. Pulling back raises the angle of attack, which produces more lift momentarily. But if you pull back and hold altitude fixed, the result is that you slow down. The wing needs more angle of attack to make the same lift at the new speed. Managing pitch, speed, and lift together is the essence of flying. Some gradients: pressure, momentum, and circulation. Engineers describe airflow with three complementary frameworks: pressure, momentum, and circulation. All three are valid and all three describe the same physical reality from different angles. The pressure explanation. Around every airfoil in motion, air pressure varies. Over the upper surface, air is accelerated, which lowers its pressure. In many flight conditions, it is the reduced pressure above the wing that is the larger contributor to lift. Beneath the wing, the pressure is generally higher. The net difference between lower pressure above and higher pressure below creates a net upward force. This is the explanation most people first hear. It is partly correct, but its popular version often relies on a misleading claim that air traveling over the longer upper surface must move faster to arrive at the trailing edge at the same time as air traveling under the shorter lower surface. That claim is false. The two parcels of air do not need to arrive simultaneously, and physics does not require equal transit time. A more accurate statement is that the wing's shape and angle force the surrounding flow to follow curved paths, which causes pressure differences. The pressure field, not any force timing argument, is what produces lift. The momentum explanation. There is a complementary view. A wing produces lift by changing the momentum of the air around it. More specifically, the wing deflects the airflow, giving the surrounding air a downward component of velocity. By Newton's third law, if the wing pushes air downward, the air pushes the wing upward. This view is popular in engineering because it is robust. Even a flat plate held at an angle produces lift, and that lift is easy to understand as a redirection of flow. The air leaves the wing differently from how it approached. It is tempting to pit these two explanations against each other. Students often ask which one is the real cause of lift. The honest answer is that they are both real and they support each other. The pressure field around the wing is the mechanism that turns the airflow downward. The downward turning is a consequence of that pressure field. In a steady flow, both descriptions describe the same phenomenon. Press your hand out a car window, tilt it slightly. The airflow is deflected, and you feel a force. That force is both a pressure effect and a momentum effect. Open your palm flat versus angled, or hold a flat board versus a curved one, and you are demonstrating the same physics that keeps a wing aloft at a scale you can feel. Circulation and vorticity. Engineers sometimes describe lift with a concept called circulation. The idea is that the airflow around a lifting wing has a net rotational character when viewed in cross-section. The air moves slightly faster over the top of the wing and slightly slower beneath it, creating a circulation pattern around the airfoil. A lifting wing is said to have bound circulation because the rotating pattern is bound to the wing. This circulation is the source of the pressure difference that creates lift. At the trailing edge, nature enforces a condition called the cutter condition. Airflow leaves the sharp trailing edge smoothly, rather than flowing around it and curling onto the upper surface. This constraint helps determine how much circulation the wing establishes. When the wing first begins to move, a starting vortex forms at the trailing edge before settling. The circulation generated behind the wing at that moment matches the circulation that persists around the wing. This is called Kelvin's circulation theorem. It is a conservation argument. The wing acquires circulation, and the starting vortex gets the equal and opposite circulation. Vorticity extends beyond the airfoil cross-section. A real, finite wing sheds a pair of counter-rotating vortices from its tips, trailing behind the aircraft like two intertwined spiral wakes. These are the same wingtip vortices we mentioned when discussing induced drag. They are not a separate curiosity. They are closely tied to the downward turning of the air, and to the fact that a spanning wing with a finite length must produce a rolling wake. Why cambered airfoils are useful. A symmetric airfoil produces no lift at zero angle of attack. Tilt it to some positive angle, and it generates positive lift. This is intuitive. It is a shape turned to the flow. A cambered airfoil is different and more powerful. It can produce lift even at zero geometric angle of attack, because its curvature makes the flow behave as if the wing were already slightly tilted. A cambered airfoil effectively carries an built-in angle produced by its arching shape. The practical consequence is that adding camber allows a wing to produce more lift at a given physical angle of attack, or to produce the same lift with less angle. That is valuable for generating more lift at low speeds for safe takeoff and landing, producing useful lift without requiring steep angles of attack that invite flow separation, supporting higher aircraft loads in a given speed range. The trade-off is that camber also tends to increase drag at some conditions and can make the airfoil more sensitive to angle of attack stall behavior. High-lift devices like flaps work, in large part, by increasing camber. They extend the wing's curvature, letting it generate the extra lift needed at slow approach speeds. Thus, camber, thickness, and angle of attack combine to define the wing's lift at any instant. The lift force, not just up. It is tempting to say that lift is the upward force. That is true in wings level flight, but the precise definition is directional. Lift is the component of the total aerodynamic force acting perpendicular to the relative wind, the airflow direction as seen by the aircraft. Drag is the component acting parallel to the relative wind. In a straight, level, unbanked cruise, the relative wind is essentially horizontal and head-on, so lift points up and drag points back. But when the aircraft banks, the wing's lift tilts with it. When the aircraft climbs or dives steeply, the relative wind tilts too, and lift is no longer vertical in Earth's frame. Over the course of a steep descent, lift may point mostly upward and slightly forward. In an inverted maneuver, lift can point below the aircraft. This is why engineers are careful to say that lift is perpendicular to the airflow, not perpendicular to the horizon. The word lift carries an everyday connotation that is essential to the concept, but the correct frame of reference is the airflow, the center of pressure and the aerodynamic center. Lift does not act at a single magical spot, but engineers summarize where it acts using two reference points. The center of pressure is the point along the chord where the distributed pressure and shear forces can be treated as a single resultant force for the purpose of computing force location. The problem is that the center of pressure moves as angle of attack changes. This makes it awkward as a building block for analysis. The aerodynamic center is a more stable reference. It is the point about which the pitching moment of the airfoil does not change with angle of attack over the normal operating range. The aerodynamic center is useful because its location is nearly constant. Engineers use it, along with the aerodynamic center pitching moment, to predict how changes in angle of attack alter the nose-up or nose-down tendency of the wing. Every airfoil has a pitching moment, a tendency to rotate about its span-wise axis. For a cambered airfoil, the wind may act at a location that produces a nose-down moment. Typically, the exact behavior depends on camber and angle of attack. The wing's contribution to pitch is one of the main reasons an airplane needs a horizontal tail. The tail provides a balancing force that keeps the aircraft from tumbling nose over tail or vice versa under load. Think of a seesaw. The center of gravity is the pivot. The wing's lift creates a moment about that pivot, and the horizontal tail creates an opposing moment. Balancing those moments is what we call trim, stagnation, pressure recovery, and the flow around the wing. A useful way to understand the wing's pressure field is to follow a streamline, the path traced by a small parcel of air as it moves over the wing. At some point near the leading edge, the airflow slows abruptly to a halt at the stagnation point, where the local velocity is zero and pressure reaches its highest local value, called stagnation pressure. The location of the stagnation point shifts with angle of attack. Higher angle moves it downward along the leading edge. The air then divides. Some flows over the top, some under the bottom. Over the top, the air accelerates, pressure drops, and the flow reaches a region of minimum pressure before decelerating toward the trailing edge in a region called adverse pressure gradient. Beneath, the flow behaves oppositely. The upper surface acceleration and the lower surface behavior together create the pressure difference we recognize as lift. Approaching stall, the limit of the pressure story. As angle of attack increases, lift first grows, but eventually the flow can no longer remain attached to the upper surface. The air stops following the surface, the adverse pressure gradient wins, the boundary layer separates, and lift falls sharply. That is the stall. The stall is not a loss of all lift in the sense of zero force. It is a breakdown of the smooth flow that was producing lift efficiently. Lift may still be substantial, but it drops from its peak, and the aircraft may pitch down, buffet, or behave oddly. A wing approaching stall produces a lot of lift, but it does so with the airflow close to the edge of staying attached. Full understanding of the stall depends on boundary layers and angle of attack behavior, which we will treat in their own lesson. For now, the key link is this: lift does not increase forever as angle of attack rises. There is a maximum lift condition beyond which the flow separates. Thrust is not lift. A reader note: if you have ever heard engines move the airplane and wings lift it, that is broadly true for a conventional airplane. Thrust moves the whole aircraft forward. The wings convert that forward motion into lift. A single object, a rotor or propeller, can do both at once on a helicopter or drone, which is part of why they are mechanically different from fixed-wing aircraft. Momentum, reaction, and a hand in the wind. Let me give you an intuition-building experiment you can do anywhere. Stick your hand out a car window at highway speed. Hold it flat and level. You feel some pressure, but relatively little force, and air flows over and under your hand symmetrically. Now tilt your hand slightly upward, palm into the wind. You feel a strong upward push. Increase the tilt further and the force grows. Tilt too far, and the smooth push becomes a shaky, turbulent flutter as the flow separates. That flutter is your hand stalling. At moderate tilt, your hand is operating like a lifting airfoil. The airflow is deflected. Pressure differs across your hand, and you feel a force perpendicular to the flow. This is a direct, physical experience of lift, momentum transfer, and stall, all in a few seconds. Circulation, a subtle contact with lift. If you have seen the phrase lift is proportional to circulation, the proportionality is the Kutajoukowski theorem. In an inviscid, incompressible flow, lift per unit span equals air density times airspeed times circulation. This result is elegant and foundational. It says that the primary way to get more lift is to move faster or generate more circulation. Circulation, in turn, is set by the airfoil's camber, the angle of attack, and the Kutta condition at the trailing edge. For a reader building conceptual understanding, the theorem name is worth remembering not because you will calculate with it, but because it explains why lift scales with speed, density, and circulation. Working through a worked example, let's connect the concepts with a straightforward example. A typical general aviation airplane in cruise. The wing is cambered and moderately thick. The aircraft flies at a modest airspeed at some altitude. To cruise at constant speed and altitude, the wing must produce lift equal to the aircraft's weight. The pilot adjusts pitch so the angle of attack is whatever is needed to produce that lift at the current airspeed and air density. The camber means the wing produces lift even though the angle of attack is small in level flight. As the aircraft burns fuel and becomes lighter, the pilot may reduce angle of attack slightly or climb to a lighter aircraft altitude. Both reduce the lift required. Now change conditions. Imagine the aircraft is slow, heavy, and flying high on a hot day. More angle of attack is required because air is thin and speed is low. More drag exists because the wing is working hard to produce lift. More thrust is required to overcome that drag. If the required angle of attack exceeds the stall point before the wing can produce enough lift, the aircraft cannot maintain level flight at that speed and altitude. This is the real sense in which lift equals weight is a constraint, not a gift. The wing can produce only so much lift at a given speed, density, and configuration. Sweeping up the lesson. Lift is not a vague miracle. It is a force produced by a pressure difference over the wing, which itself comes from the wing's shape and angle of attack. A cambered airfoil produces lift at 0 geometric angle. A symmetric one needs positive angle. Either way, the wing turns airflow, creating circulation and a pressure imbalance that yields an upward-directed component of aerodynamic force. The essential points to remember: an airfoil is defined by camber, thickness, chord, leading edge, and trailing edge. Angle of attack is the angle between the wing chord and the relative wind, not the horizon. Lift is perpendicular to the airflow. Drag is parallel to it. Two complementary explanations: pressure differences and momentum/deflection of airflow both describe the same physical lift. The popular equal transit time claim is incorrect. Air over the top does not have to match air under the bottom in arrival time. Camber lets a wing produce lift even at 0 geometric angle of attack. The aerodynamic center is the stable reference point for the wing's pitching behavior. The center of pressure moves with angle of attack. A lifting airfoil carries bound circulation, constrained by the cutter condition at the trailing edge, and sheds a starting vortex and trailing wingtip vortices. Flow eventually separates at high angle of attack, which is the stall. Pressure, momentum, and circulation are three valid ways to describe the same effect. Next, 1.3 Wings and lift. Stall and high lift devices examines what happens at the edge of that maximum lift, how designers shape wings to avoid nasty stall behavior, and how flaps and slats let aircraft fly slowly for takeoff and landing.
And that brings us to the end of this episode of the Drone Builders Collective. Thank you so much for hanging out and building with us today. If you enjoyed this episode, please take a quick second to like, subscribe, and leave us a review on your favorite podcast app. Your reviews help other builders find our hangar and join the crew. Don't let the conversation stop here. Leave a comment on your favorite app or send us an email with suggestions for future episodes. Keep your batteries charged, your props balanced, and your mind curious. Until next time, clear skies and happy building.